I'm going to kick off here with a quick formal introduction, and then we can get into the meat of the real conversation today. So we're talking to Jon Stephens, who is the CTO of Veridise, on the topic of building a ZK application with o1JS. And o1JS is the SDK that o1Labs has released. I'm Phil Kelly. I lead business development at o1Labs, and I'm here with my engineering colleague, Florian Kluge. We're planning on talking for about 30 minutes before opening up the conversation for wider participation. And excitingly, Jon just published the code that we're talking about here, GitHub. So that's exciting. We'll probably drop the link into Twitter later. And yeah, it's really great work, Jon. We've seen partners obviously build SDK-based code to POC level and even beyond. And yours is really great and very rich. So we appreciate the work there. All right, so just a little bit of background. This is the first in a new series of weekly Twitter Spaces with projects in the o1JS Partner Program. The Partner Program is here to help existing Web3 projects as they get experience building ZK applications. And you may already know, but just a reminder, ZK applications are applications where you can build code that runs on the client side. So built on the client side in ZK code, and you can then execute it and prove correct execution back on a blockchain. And so that's how you get privacy, for example, in the Web3 world finally. And it's also how you avoid gas costs and latency and data challenges that we've seen that working entirely on chain can bring. But on the other hand, it's still trustless. So that's the thing of the applications. It's kind of a new construct to the Web3 world. And so, it's hopefully it makes sense from a conceptual level, but we really want to bring it to life with some practical examples. So that's what we're trying to do with this series of conversations and also with our work around the partner program. And then just a quick reminder for anybody who's new to this as to what o1Labs does. So first of all, we built o1JS, the SDK that allows you to build client-side ZK applications. And we made a big focus on making it highly usable both for developers and users. So on the developer side, you can develop with TypeScript, and it really is TypeScript. It's not a derivative of it. So that means that you can use TypeScript tooling. It's a high-level language, so you certainly don't have to be a cryptographer. And we've seen people build proof of concepts, like good proof of concepts, in 20, 30 hours with our help. It has recursion built in, and it deploys without trusted setup. So you can build ZK app and deploy it immediately, and you can make changes and redeploy it. So it's a really good developer experience, we believe. And then from the user's perspective, you can deploy in a browser. You can run in a browser. It deploys with WASM. So that means as a user, you can keep all your data private locally, and you can just send statements about your data to somebody else, and that's how you get privacy. You can also run it on a server, and that's probably a more realistic scenario for some of the use cases that we're talking about. So we built o1JS. We're also the engineering team behind the MENA protocol, which was the first ZK-based L1, and is now in the late stages of testnet for an upgrade that will make it a greater verify and settle the ZK applications that you can build with o1JS. And then finally, I'd say we're looking at new approaches to client-side ZK. So far, we've been focused on circuits, but people have probably heard about ZK VMs, so we're starting to do some work around that. And a good example of that is the work that we're doing with Optimism to put their fraud-proof engine, their fault-proof engine in a ZK wrapper. And the results of that should be very synergistic with our work on MENA's ecosystem and roadmap overall, and should extend the use of our Plonkish proving system in the market. Okay, so that's the introduction. Thanks for bearing with me through that. And let's turn to Veridise. And Jon, I should say that the application you built here, which is for proof of liabilities to help accounting integrity issues, it's actually not your core business, is it? So I'd like to let you introduce yourself and talk a little bit more about Veridise and what your motivation was for building with this code.
Sure. So Veridise is actually a security company. And so what we mainly do is many of the people at Veridise, including myself, come from a particular area of academia called formal methods, where Usually what we do is we're developing infrastructure that is capable of identifying bugs within software in a way that is mostly automatic. And so that's typically what we do. Here, though, uh, we basically wanted to learn more about the ecosystem, and typically when we do so, we need some way of engaging with that ecosystem. Typically, this is by reading documentation and by developing some small model applications. And so for most of the ecosystems that we've engaging with, we've developed similar, small model applications in order to get a better idea of the language features and the potential pitfalls that there might be for developers. But this is the first time that we've really made it available. In the past, typically these model applications we've used as challenges, both internally and at workshops that we've hosted, like at Securium, rather than as actual applications that we're releasing publicly. So this application is a proof of liability app. And so essentially what a proof of liability is going to do is when you're working with an exchange, typically an order book exchange, when users end up depositing their funds on that exchange, that exchange now has a liability to that user. And so we've recently seen a lot of exchanges post a proof of solvency. And a proof of solvency is going to include both a liability, which is going to be the funds that are owed to users, as well as the amount of funds that they have, which prove that they can cover all of their liabilities. And so this particular portion is just that liability part where an exchange can then take this and create a proof of solvency by adding in information about their funds. And so if all of their funds are living on the blockchain, then obviously this becomes very easy. The harder part has to do with funds that live off of the blockchain in fiat currency. And so what we wanted to do is, currently the way this is done is exchanges will post information about their solvency relatively infrequently. So this is typically because or posting this on a blockchain is typically expensive, because if you try to post all of this information on a blockchain, every single time someone interacts with your exchange, you're likely going to be incurring a lot of fees. And so that's one thing that we've tried to address. But also the logic corresponding to the proof of liability has to be designed in such a way where it takes into account the possibility of the exchange trying to reduce their liabilities, as well as users trying to prove greater liabilities. And I think we'll talk about the threat model, which is what this corresponds to, a little bit later in this discussion.
Thanks. So accounting is kind of a dry subject, but this is actually kind of an interesting construct, right? Because you're essentially allowing a user to see a total liabilities figure that an exchange has published, and without actually seeing they'll prove that what's owed to them is including that liability. Is that a fair representation?
Yeah, yeah. And it's kind of a protocol in order to hopefully keep all parties honest.
Yeah, like adversarial.
Right.
And so the interesting thing about this is that even its existence, I think, creates a very strong incentive for the exchange to be honest. They don't know which users might prove their balances, and so it's kind of high jeopardy honest all the time. So you don't need everybody to prove all of their balances all the time. You just need some users, and random factor in there to prove their balance sometimes, and then you've got a big disincentive for the exchange to cheat.
Right. So just to give a little bit of context about how this works, basically, Exchange is going to post something called the liability tree, which is going to be a Merkle tree with information about account information. And then typically, a user can then go in and actually ensure that their account information is up to date in this tree. And so we've seen a couple of exchanges uh, use this method in the past in order to show users that, yes, the exchange is actually accounting for their funds correctly. But like I said previously, it typically is not something that um, is updated frequently or with quite as much clarity, or because the code is not hosted on the blockchain. You can't go and actually inspect the code yourself.
And just in terms of practicality, I mean, there's probably a number of ways in which this could be administered, but a user could, for example, that their login process could trigger that the proof that the balance they see is included in the total liabilities figure, or I guess there could be a standalone application or widget that just allows the user to go and prove on an ad hoc basis that they're still counted.
Right.
Yeah. And, before Florian's going to talk a little bit more with you about the technical approach and some of the details and, experience of using o1.js. But before we do that, I was just going to say a lot of the conversation in the market has been very specifically about centralized exchanges and, the issues that we've seen with them. And as you pointed out earlier, this is kind of a two-sided equation. There's proof of liabilities and there's proof of assets. And I actually think proof of assets has got a lot more attention because it's very directly Web3. Proof of liabilities is actually a Web2 issue. Like the books and records are off-chain, and so it's a really interesting use case that is useful for proving the integrity of the finances of a centralized exchange, but is massively generalizable. And there may be uses for this in accounting and auditing in the Web2 world in general. So, for example, you might trust a large business to be that's regularly audited to be correctly stating things about its accounts. But if you're dealing with small and medium-sized businesses as a counterparty or a customer, you might, for example, in the future want them to prove things with ZK without requiring them to go and send you the whole books and records. And that may not be an industry that sets the world on fire with excitement, but it's huge. I think the Web2 financial auditing business is somewhere, I've seen figures between 50 and $150 billion a year. So the applicability of this, although it's like very specifically a centralized exchange use case in the framing in the Web3 world, I think is enormous. So yeah. Shall I let you guys talk a little bit about the architectural approach here? I'll hand over to Florian.
Yeah, thank you very much. And thanks, John, for joining us on this bit of space today. So you published the code of the proof of concept, and I think we will share the link later so that the people who are interested in the technical implementation can take a look as well. But yeah, so while you were working on the proof of concept, you worked on essentially two different approaches. Number one being a smart contract only focused approach, and the second one being a combination of recursive proofs. Can you talk us through the implementation about the disadvantages and the differences between both of these approaches and just overall your thought process?
Sure. So just as a bit of a disclaimer, the code that's going to be posted later is still under development. The main thing that's in there is the actual liability. But there's a list of things that I have yet to implement yet, which would hopefully be available before anyone started using this. However, as Florian said, there are two aspects to this. So it's just a liability proof that lives in the smart contract, and another case where you're modifying it using a ZK circuit. So in the smart contract case, which is what I'll start with, basically what you have is you essentially just have a Merkle tree. And with that Merkle tree, you're allowing certain users, in the case of what is posted online, it's just the exchange, to update that Merkle tree with information about actions that were performed on behalf of the user. So essentially, a user will sign an action that they want to perform, such as depositing funds, withdrawing funds, swapping funds, and so on. And then with that signature, the exchange can then check this in, and that will modify this liability tree to give an accurate accounting of those funds. And then what it also allows the exchange to do is, because they have now updated the blockchain with this information, they can then provide the user proof that their balance is correctly recognized within this on-chain Merkle tree by just giving them the path from the Merkle root to the leaf of the user that corresponds to their account, and then the user can validate that yes, their account information is correct. The problem that you can run into with this is it really requires the exchange to interact with this on-chain Merkle tree every time a user performs some interaction with the exchange. And so in that case, the exchange is incurring fees every time, and obviously that would be not ideal for a lot of reasons. One, most of those fees are probably going to be passed off to the user, and so on. And so the ideal case would be to allow the exchange to update this tree less frequently. So like once a day or once every few hours or something like that. Doing so with an on-chain only approach, however, requires that the Merkle tree modifications are somehow bundled. And bundling those modifications and validating that only modifications that came from the user can be difficult, because you then have a lot of signatures that might need to be checked and so on. And so this is where the ZK proof comes in. And so instead, in this application, there is a version that will allow the exchange to interact with this ZK proof and say, okay, this is the current state of the Merkle tree that I have off-chain that I am going to check in. And it proves that the exchange correctly updated the tree according to this interaction that the user wanted to perform. And then the exchange can provide proof that they updated the tree correctly to the user as some sort of a receipt. And so in this case, the exchange is going to be generating these receipt proofs, which is what they're called in the application. And over time, when the exchange wants to check everything in, they just need to bundle all of those up, which is what the rollup ZK proof does, which is just a recursive ZK proof, which will verify that, yes, the receipts are correct, in order to take all the receipts and bundle them up into one, and then they check that into the smart contract. And so at that point, all the smart contract needs to do is say, yes, I know that this came from this particular ZK proof, so it verifies the verification key and validates that, yes, this came from this proof, so therefore I know that the tree was updated in a way that was consistent with the intended behavior. And then once it does that, it can simply update everything in one go, and users can therefore trust that, yes, when the tree is updated in this way, everything was actually updated in a way that is consistent with how the liability tree should actually be updated. And so it allows fees to be more distributed, because everyone who interacts with the exchange over that entire day would essentially get a small portion of the fee to update this this liability tree, rather than the exchange charging everyone for every interaction. So, it basically just makes everything a bit more distributed and a bit more clear as to how the exchange is actually performing these updates.
Thank you. Yeah, so recursion is something I'm personally very excited about, and I think this particular use case, especially leveraging recursion, is a really interesting sort of like example that people, or like that you can use o1.js for, because recursion is at the heart of o1.js, and not only of o1.js, but also at the heart of the Mina protocol. And recursion, especially the proof recursion of taking a proof and then recursively verifying it within another proof, and sort of like doing that over and over again, is something that is very unique and not really a lot of CK toolkits offer currently. So I really like that system, and utilizing that in applications, and simply leveraging the power of efficient off-chain computation, distributing the fees and the costs, just simply making incremental state updates more efficient overall. So, given your experience with other CK toolkits, DSLs, especially with the recursion part now, I'm curious, is there like anything you can talk about a bit more about the recursion part in o1.js? How was your experience using recursion? Was it easy? Was it difficult? So, yeah.
Yeah, so using recursion with o1.js was very easy. There are obviously other ZK protocols that we have worked with in the past that support recursion. So I believe for a while, for example, Circom didn't support recursion, but now it does. And then obviously there are some others that rather than supporting recursion, instead support folding. So now we're talking about Fry-based ZK approaches. And so in this case, though, the ability to verify other ZK circuits very easily did come in handy because, basically when you pass a proof into another circuit, you just have to say, verify that proof. And as long as you do so, it does make it easy to actually perform recursive verification, not only for a single type of ZK proof, but for other types as well. And so this is something that I had to take advantage of when designing this application.
Thank you. Yeah, that's very interesting. So looking at o1.js a bit more in detail, for those who don't know, it's a CK DSL, embedded DSL framework for TypeScript. So I'm curious to know if you have any previous TypeScript experience, and how your experience was going into o1.js. Is there like anything that you had to relearn from scratch? Could you leverage previous CK-DSL experiences? Did you have to learn TypeScript from beginning? What was your overall, I guess, experience getting started?
Yeah, so in terms of TypeScript, I have used TypeScript in the past. To be honest, it's not one of my favorite languages. It's better than JavaScript, but I really hate JavaScript. Uh, so using TypeScript was um, not that bad because at least it's a strongly typed language. Using o1.js worked relatively smoothly because you are interacting with a high-level language with concrete types, which is always helpful, in my opinion, at least. And so, yeah, everything, at least at the TypeScript level with o1.js, was very smooth. It was very well integrated into TypeScript, where it didn't feel like I was interacting with another language. It was a TypeScript API that I was interacting with and passing around TypeScript objects. In terms of comparisons to other languages, obviously Veridise has worked with a lot of ZK languages in the past, like I've already mentioned Circom, Halo 2. We started looking into or working with Plonky 2 now as well. And so it bears the most similarity to another language, or to languages like Circom, because with languages like Halo 2 and Plonky 2, you're now interacting with Circuit Builder in Rust versus actually expressing your ZK circuit more directly. And so at least in when compared with Circom, there are a lot of concepts that are similar, where you're expressing your witness generation code and your constraints side by side. And so, yeah, it's very similar in that way to other like CIRCOM, where you have a higher level language to directly express a circuit along with, constraints and witness generation code.
Yeah, I mean, I definitely have to agree that JavaScript is an awful language, and I'm very grateful for TypeScript. It makes everything much more easier having concrete types, knowing what data types you're dealing with. So that's a very big benefit. So before we get a bit into, I guess, like security questions, and like how people, like what people need to know about security, I have one more thing I'm interested in. Did you work on the project by yourself? Did you have anyone else helping you? And how many hours did it roughly take for you to get started and then finish or like get to the current state of the proof of concept?
Yeah, so I've been working with other people at Veridise on this. So a couple of them, I believe, are listening to this call, including Kostas and Ben Sapansky. And so basically, the way it started with Kostas, Ben, and I discussing the threat model, specifically about how an exchange might try to, let's say, reduce their liabilities. That way, they can more easily prove solvency versus a user wanting to possibly inflate the liability of an exchange just to ensure that they have sufficient funds to actually pay the user back. Because the more funds that the exchange needs to keep, the better the chance that no matter what happens, the exchange is going to be able to pay users. And so I discussed the threat model with them. On the development side, I've mainly been the one who's actually been developing the code. And so, yeah, in terms of the amount of time that it's taken, a couple of days working with Ben and Kostas to converge on a threat model that we were happy with. And then after that, I would say that I've probably spent maybe like 30 hours or so working on the implementation so far. And as I said, it's not quite done yet, but the main liability proving stuff is there.
Yeah, awesome. Yeah, it's always cool to see developers getting hands-on experience with a new framework like o1JS and managing to build something substantial, even though it's not finished yet. I think it's still in a very good state, in just, like a relatively decent time frame. So I think now we are getting into the exciting part of the Twitter space and talking a bit about security and your expertise. Given that you and also Veridise, you have extensive hands-on experience with CK DSLs, CK proof systems, and frameworks, and all that stuff. I'm curious to learn more about what are some common pitfalls and potential errors that people do over and over. Is there like a common pattern that people follow, and how can we prevent developers from making these security errors in their applications?
Right. So one of the main ones that we see in almost all ZK language is the potential for defining under-constrained circuits. So just to give a brief introduction into this type of vulnerability, basically what an under-constrained circuit is going to be is it's going to be a circuit where the constraints that are being declared are more permissive than the witness generator. So basically, all of the input-output pairs produced by your witness generator would be accepted by your constraints, but there might be outside the behavior of your witness generator that would be accepted as well. And so what this allows is for someone to essentially generate an alternate witness that would never be generated by your code, but they can still provide that to the verifier and or to the prover in this case, and the prover would still prove that it was correct because it's still consistent with the constraints, and then it would get verified. And so this is something that can happen with o1JS. So a quick example for people who are familiar with o1JS is when you're using a state variable, for example, you have to first retrieve that state variable, and then you have to prove that the variable retrieved is consistent with the variable that is on chain. If you forget this, then you can have an under-constrained circuit where if you do not verify that the version that lives on chain is equal to the version that you have checked out locally, essentially what could happen is someone could design an alternate witness generator where what you have checked out locally is not what exists on chain, and then use that and basically use that value throughout the circuit, and it would still be validated because there is no constraint that actually says these two things are equivalent. And so that would be one example of how you might, get an under constrained circuit in this case. There's also other bugs that could potentially pop up. So for example, missing validation is something that might happen where if someone is using a recursive ZK proof, they have to make sure that they still verify it and not just use the declared inputs and outputs, because if they aren't verifying that the proof is actually correct, it could be the case that someone passes in a dummy proof. And so that could be another area where people run into issues. And then just to mention very quickly is there currently are no checks, that involve checking for overflows or underflows of the field. And so what this means is similar to cases that we saw with Solidity a couple of years back for Solidity 8. You could have cases where someone tries to prove something, but because of an underflow, they are able to, let's say, take a very small balance and then prove that they actually have a very large balance because they underflowed or caused a particular value to underflow. So protections like this all need to when people are designing their applications, and it's part of the reason why we always strongly suggest that people undergo a security review before actually using their code. And so one part that we will do eventually with the proof of liability, once it's a bit more mature and I've finished the development of a couple more aspects that aren't quite there, which are indicated in the repository, is I will have other people at Veridise perform a security review of it just to make sure that I didn't make these mistakes, because they're very easy to make.
Yeah, I think especially in CK programming, there is always a trade-off between doing too many constraints and sort of like sacrificing efficiency versus not doing enough constraints and then sacrificing security. So just to give a bit of background information, I guess some things that we are exploring to make these things just more easier for developers, for example, linting, providing linters that explicitly tell the developer if there's anything that's wrong with their circuit, if there are values that are unconstrained or not constrained correctly. We are actively exploring, like overall making the API more verbose, obviously like making it easier to understand for developers what exactly is happening with the code they're using. So there's a couple of measurements we are taking, but I'm also curious to know if there's like anything you recommend developers that maybe apply to not only o1JS, but the overall CK ecosystem. Is there anything a developer can do today to make their code more secure? Is there like a 5-step guide to build secure applications? Is there like anything you want to point people to, except an audit, which obviously is a very important next step, but within their development phase, what could people do to write secure code?
Right. So writing secure code is always very hard, and it gets even harder once you move to ZK. So obviously one thing that developers should do is just write tests. Testing is a very powerful tool. The only part once you move to ZK is testing won't necessarily show you that you have an under constraint circuit, because like I described previously, in order to find these under constrained circuits, you need to work with a different witness generator. And so Testing is very powerful to find some of these other examples of vulnerabilities that I described. So testing could help you find overflows or underflows. So always make sure you're testing with a variety of values, including large values or very small values. Test with 0, just because, you know, 0 in a lot of cases ends up causing issues in code that doesn't expect it. And also, one thing that I'm currently working on in the testing infrastructure that is available in the proof of liability stuff is performing random testing. So, for example, not testing with concrete values, but using randomness to hopefully improve the coverage throughout the code in order to ensure that a variety of values are actually going to be covered. And then obviously also test against positive cases as well as negative cases. So ensure that things break when you expect them to break, and that when transactions actually are verified or they are accepted, that the output is expected. In addition to that, it's always useful to make use of other tools that are available. So because this is in TypeScript, making of a variety of linters is always useful. Taking advantage of fuzzers, which I don't know if there's one currently available for o1.js, but you know, basically taking a look around and seeing what tools are available to help point out potential issues and to just improve your style in general, because when it comes down to an audit, having good style can make it easier for the auditors to find potential bugs in your code.
Awesome. Thank you very much. Thanks, Jon, for joining Twitter Space and working with o1.js. It's very interesting getting someone from the security space and CK security space to work with o1.js, getting your perspective. So I'm very grateful for that. Thank you. I'm throwing it over to Phil. Is there anything you want to talk about?
Yeah, just to reiterate that, thanks very much again, Jon and Veridise, for the work here and the insights. I mean, like I say, it's a really interesting use case. You know, don't be put off by the word accounting, because this is, number one, I think this has applicability to an enormous industry. And number two, the construct here is really cool. I mean, allowing individuals to use inclusion proofs to show that you know, what they're owed is included in the balance. And then I really like the fact that this is using recursion to greatly reduce the cost of verification, and allowing proofs to be batched up. So, you know, all of those are extremely powerful approaches to using ZK in action. So yeah, we'll throw it open for any questions or comments here. I would just say, in case we run out of time, so first of all, you know, we have o1.js available to download. We'll tweet a link to that. And then also, we're rolling through partner cohorts. Very keen to hear from other projects that are interested in building ZK aspects to the applications that they've got, or even brand new applications. You know, it could be a privacy use case. It could be general verifiable chain computation. So please feel free to reach out to me on Twitter. And then the last thing I'll say is that we have a series of these talks now, these spaces, over the next 4 or 5 weeks. So if you want to tune in again, same time next week, we're going to talk to Snickerdoodle about their use of ZK applications in o1.js for building privacy in a construct they have for a building alternative to Web 2 cookies. Look out for links to the SDK, and also please join us next week around the same time to talk with o1Labs. Thank you.
Thank you.
Yep, thank you.
Thanks, Jon.